Hello everyone. We are on 2.6, section 2.6. We're really looking at exponents, or they're called powers in the book at this stage because we're following on the power variations, so they're keeping that word alive. Alright, we were good at looking at patterns last chapter. Remember that inductive reasoning where we looked and observed patterns. If you look at this pattern, it's pretty clear what's going on here. It's getting to be half as big each time as we go left to right. I'm working in the other direction because we arrange bigger numbers on the right in our number line. So you'll see why that works in a minute. If we write each of these numbers as a power of 2, right, we can write this as 2 squared. That's an easy place to start. And this is 2 times itself 3 times. And with another 2 to double it, that's 2 times itself 4 times. Here's then 2 times itself once. So if we just simply look at these exponents, 2 times itself 4 times, then 3 times, then 2 times, then 1, to keep this pattern going, it really makes sense if we write this as 2 times itself no times. Or if we think of dividing by 2 each time, this then is 2 divided by 2 gives us 1. If we keep this pattern going this way, we'll see that half of 2 is 1, half of 1 is 1 half, half of 1 half is 1 fourth, and then we can go half of 1 fourth is 1 eighth. And if we keep this number going down 1 each time, it makes total sense that from 0 we go down 1 to negative 1, we go down 1 more to negative 2, and we go down 1 more to negative 3. So if you just simply look at this part of it, we've got 2 to the negative third equaling 1 eighth. Well, 8, as we found right here, is 2 to the positive 3, so we can write this as 1 over 2 to the third. All right? So this gives us one of our first key definitions for this section, and that is that any number, not just 2, but any value of x to the negative n is going to be equal to 1 over x to the positive n. In our case, the base number here, x, is 2. So write this down, get comfortable with it, look at this pattern until it makes sense to you. But a negative exponent is not like a negative number that's being multiplied. It's really dividing by that number a certain number of times, just like an exponent here is multiplying by that number a certain number of times. Okay, so that's definition number 1. Another thing that just I want to make clear is that there's the basic laws of exponents, right? If you ever asked, what is x to the third times x to the fourth, and you're not sure, think about what the definition of an exponent is. This is just x times itself 3 times. This is just x times itself 4 times. So it makes sense that this equals x to the 7. And you quickly will remember that the rule is you just add those 3 plus 4. All right? So we have our laws of exponents like x to the m times x to the n is equal to x to the m plus n. All right, x to the m then raised to the nth power. That would be like saying, well, what is x to the second raised to the third power? Okay, pause the camera if you want and think about that. What it's going to be then is if we've got x to the second raised to the third, that's going to be x times x, that's x squared, multiplied by itself 3 times. So we'll have x times x and x times x, because by definition, we've got x squared times itself 3 times, all right? So that equals then x to the 6th, or in this case, if I think of it in general terms, it's x to the m times n. So we multiply when it's in an exponent, like in a parentheses like that. We add when they're next to each other. Those are the 2 fundamental rules you need to know and get really used to them because you'll be applying them over and over again. All right, well, this will lead us to our second big definition, all right? If you think about it, if I take the square root of x squared, I simply get x. Does that make sense? If I then think about, well, if I have x squared raised to some mystery exponent, that's a 2. If I raise that to a mystery exponent, call it n right now, and that's equal to x, well, x is just x to the 1, right? So if I want to somehow think of an exponent that will undo squaring, and will get me back to my simple original x, then this rule here that says I multiply them, it must mean that x to the 2n, when I multiply 2 times n, is going to be equal to x to the 1. And if I simply look at these exponents, I can solve, and I say, well, what number times 2 gives me 1? Well, the only number that that works for is 1/2. So I can say that the square root of x, right, is the same as raising this to the 1/2 power, because if I multiply these, I get x to the 1, or just x. So our second definition then, I'm going to erase these. Our second definition is that x to the 1 over n is the same as the nth root of x. That when I take the square root, the second power root of x, that's the same as 1 over n. If I want to take the third root of x, that's the same as 1 over 3. All right? The square root is 1 over 2. Okay, I think I said that incorrectly. So you will see in your book there are a lot of examples that have you work from what's called radical form to exponential form, or go from exponential to radical form. You'll see there's some problems that go from, oh my goodness, lights out, back on. That's the power saving feature here at Pingree. Negative exponent to a positive exponent, but written in the denominator. All right? So I'll do one example. The power usually goes out in about a minute. We'll see if I can sneak it in. All right, so in the book, they will say, like, write a certain fraction without negative exponents. And it might be something like this. It'll say simplify. Okay, it'll be like 2x to the 0, y to the negative 3, all over 4x to the negative 2, y to the 6, something like that. And you've got to make sense out of that. All right, remember PEMDAS, that parentheses come first and then exponents. So this exponent applies first to the x before we do the multiplication, and x to the 0, anything to the 0 power is 1. So this just goes away and becomes 1. Anytime you see a negative exponent, you can take that and you can write it underneath, draw that fraction bar, and now this will go down below. Anytime you see a negative exponent below, you can write that up above, and that's going to go up there. And then anything else just sort of stays in its place, and then you use the rules to, that's y to the 6th, okay? And now we'll simplify that. Well, this is the rule that if they're the same base, we add those. There's no other x's, so this would just become x squared over 4y to the 9th, okay? So that's a typical example, all right? So I will put a little practice problem for you and a little quiz up on Moodle, and give it your best shot, okay? Good luck.